performance. Welcome to the lectures of high performance computer architecture. Previously we have seen in computer organization and architecture that how various functional units are organized in a computer and how different software and hardware set interact with each other to form a computer system to execute a program. Now in this very course we will learn what are the various technologies and architectures to enhance the performance of a computer system. That is, our aim is to improve the performance of a computer. So our discussion starts with the basic idea of performance. So performance is basically a measure of how fast a computer executes a program. If E is the execution time of a program, we can say the performance is inversely proportional to E. It depends on the design of hardware, the machine language instruction and the compiler. Next we have some terminologies. First one is response time. So it is the total time taken to execute a program, that is time taken between start and completion of a program. It depends on all the units of computer, that is input, output, disk, processor, etc. Next is CPU time. The time for which CPU is active only while executing a program. It depends only on the processor and hardware involved. Next we have throughput. So throughput is defined as the number of instructions executed per unit time. It is measured in terms of instruction per second or MIPS, that is million instructions per second. Next is clock cycle time. Every processor is controlled by a clock signal. Time taken for one clock signal to elapse is called clock cycle time. Next is clock rate. Clock rate is simply reciprocal of the clock cycle time, measured in terms of hertz. Next we have basic performance equation. So in basic performance equation we calculate CPU time. CPU time can be calculated as the total number of clock cycles required for a program multiplied by clock cycle time. Now total number of clock cycles can be calculated as number of instruction in a program multiplied by clock cycles per instruction. So CPU time will be instruction count, that is number of instruction, into CPI, clock cycle per instruction, into CCT, clock cycle time. CCT can sometimes be referred as 1 upon clock rate. Now we have a question. Two machines M1 and M2 having clock rate and clock cycle per instructions as 50 MHz and 2.8 cycles and 75 MHz and 3.2 cycles respectively, working on the same instruction set. Which machine is faster and by how much? So for M1 we have clock rate as 15 to 10 to the power 6 Hz, CPI as 2.8. For M2 clock rate is 75 into 10 to the power 6 Hz and CPI as 3.2. So time for machine 1 will be instruction count into CPI upon clock rate, that is IC into 0.056 into 10 to the power minus 6 seconds. For M2 time will be IC into 0.042 into 10 to the power minus 6 seconds. Since both machine works on the same instruction set, IC will be same for both the machines, hence M1 is faster. Next we have a program is executed for 1 second on a processor with clock cycle of 50 nanoseconds and throughput 15 MIPS. Calculate the CPI of the program. So time is 1 second, clock cycle time is 50 into 10 to the power minus 9 seconds, throughput is 15 into 10 to the power 6 instruction per second. Now throughput is equal to number of instruction per unit time. So instruction count, that is number of instruction, will be throughput into time, that is 15 into 10 to the power 6 instruction. Now CPU time is equal to instruction count into CPI into clock cycle time. So CPI will be time upon instruction count into CCT. Hence CPI will be 1.33 cycles per instruction. Next we have a question. Consider the following table regarding two different processors P1 and P2. So two processors are given, their clock rate, number of instruction and execution time are given. Find out IPC, that is instruction per cycle, for each processor and compare their performance. Now we know CPU time will be instruction count into clock cycle per instruction upon clock rate. So CPI will be time into clock rate upon instruction count. For processor 1 CPI will be 0.7, processor 2 CPI will be 0.5. Now we have to calculate IPC, instruction per cycle. So instruction per cycle will be reciprocal of clock cycle per instruction. Hence for P1 IPC will be 1.4, for P2 IPC will be 2. Now we have to compare their performances. So performance is compared on the basis of IPC or CPI. So since CPI of processor 2 is less or IPC of processor 2 is more, we can say performance of processor 2 is better. Now speed up. So if we have a system and we have made some enhancement on it, Let PWEW be the performance and execution time of the system without enhancement, and PEEE be the execution time and performance of the system after enhancement. So speedup is defined as performance of the system with enhancement upon performance of the system without enhancement. Since performance is inversely proportional to execution time, we can say this speedup is also equal to execution time of the system without enhancement upon execution time of the system with enhancement. Next is Amdahl's law. It states that the performance improvement to be gained from some faster mode of execution is limited by the fraction of time the faster mode can be used. This law is used to find the overall speedup in a system due to some enhancement. Now, Amdahl's law uses two factors to find the speedup from some enhancement. First one is fraction enhanced, second is speedup enhanced. So fraction enhanced tells what fraction of time the computer can be enhanced. For example, if a computer takes 10 seconds CPU time and 40 seconds for input-output operations, then obviously 10 second CPU time can be made enhanced. So FE will be 10 upon 50 total time, that is 0.2. Now speedup enhanced tells how much faster a task would run using the faster mode of execution. So if enhanced mode takes 3 seconds and original mode takes 6 seconds for execution, speedup will be 6 upon 3, that is 2. Now we see fractional enhanced is always less than 1 and speedup enhanced is always greater than 1. Now the overall speedup is given by 1 upon 1 minus FE plus FE by SE. So here we have a question, what is the speedup if 90% of the program is made 5 times faster? So since 90% of the program is made enhanced, we have FE is equals to 0.90, and since the enhanced system is 5 times faster, our speedup is 5, so overall speedup came out to be 3.57. Next question, to enhance a 3D video application, a new processor is designed which is 20 times faster than the original processor. If the older processor is busy with 20% computational time and waiting for 80% of the time, what is the overall speedup gained by incorporating the enhancement? So here we have, since 20% of the task can be made enhanced, our fractional enhanced will be 0.20, and since enhanced mode is 20 times faster, our speedup enhanced is 20, hence overall speedup is 1.23. Next we have parallel computer structures. In parallel computer structures or in parallel computers, multiple tasks are processed simultaneously on multiple processors. Some examples of parallel computers are pipeline computers, array processor computers, vector processor computers, superscalar processors, super pipeline processors, and VLIW processors. Next is Flynn's classification of parallel computers. Now, based on number of instruction and data stream that can be processed simultaneously, Flynn has classified parallel computers into 4 types. Number 1 is single instruction, single data systems. It's a uniprocessor which executes single instruction and operates on single data stream. If CU is the here CU is the control unit, P is the processing element, and this is the memory. You can see the processing element executes single instruction and operates on single data stream. Next is single instruction multiple data system. It's a multiprocessor capable of executing single instruction but operates on multiple data stream. Here different processing elements execute single instruction but operates on multiple data streams. Next is multiple instruction single data system. It's a multiprocessor capable of executing multiple instructions on different processing elements but operate on same data stream. So different processing elements operate on same data stream but executes different instructions. Next is multiple instruction multiple data systems. It's a multiprocessor capable of executing multiple instruction on different processing element and operates on multiple data streams. So the processing elements different processing elements executes different instructions and operate on different data streams. So that's all for this slide. Thank you.